practice test, so you could expect that it's going to be a good chunk, or at least representative chunk, of the actual test. When you see something that's a binomial raised to a power, you want to be thinking of it as two separate factors. So x plus 6 multiplied by x plus 6. All right. Now, when you're distributing, you take your first term, multiply it by the first term of the first binomial, multiply it by the first term of the second binomial. Remember, as long as you have this idea in your head that when you have two factors, you're taking each part of the first factor and multiplying it by each part of the second factor, it's a good basis for understanding. So we're taking that x, multiplying it by x, and also by 6. If it helps, jazz this up with all the trimmings. Coefficient exponent, coefficient exponent. Remember, when you're multiplying monomials, you multiply the coefficients, but you add the exponents. All right? So 1 times 1 is 1, x squared. Then when I multiply the 1x to the first by 6, there is no x attached to the 6, so the x part of it is immaterial to the product. So all I'm going to worry about is multiplying the 1 by the 6. All right, so that's going to be plus 6x to the first. Then I move on to multiplying my second term of the first polynomial by each term of the second polynomial. All right, so 6 times 1 gives you a 6. X to the first comes along for the ride. And then 6 times 6 gives you 36. All right. Then it's a matter of combining like terms. All right. So I see two terms in the middle. Like terms are terms that have the same variable raised to the same power. All right. So when you have like terms, you only combine the coefficients. You leave the exponents alone. All right. It's a memorization piece at this point. So the x squared stays put. 6x plus 6x gives you a 12x. You can say 12x to the first if you want, but 12x. And the 36 comes along for the ride. And so that makes it, the choices should have been randomly arranged. So for me, it's the third choice. All right. Next one, similar concept in terms of the breakdown. We're going to distribute, but now we have alternating signs. All right. One sign is positive. The other sign is negative. It's important to understand that whenever you see something that's structured like this, the result is always binomial, all right, meaning a two-termed expression. So if you're going the trial and error route, you can actually pare it down to just two choices just by knowing that fact, all right? But if you need to play it out, you have the x plus 2x minus 2. All right, so coefficient, exponent, coefficient, exponent starts off the same way. 1x to the first times 1x to the first, multiply your coefficients, add your exponents. 1x to the first times negative 2, so negative 2x to the first. 2 times 1x to the first, 2x to the first, and then 2 times negative 2, negative 4. In this case, you see how the middle terms, those two like terms in the middle, are exact opposites of one another. Right? Exact opposites cancel away. All right? So you're just left with the x squared minus 4. All right? So nice, nifty little shortcut for a problem like this is first recognizing that your answer should be binomial by seeing that you're looking at two factors that are each roughly identical, except the middle term is the opposite. All right, or the middle sign, sorry, is opposite. All right, so you know it's going to be binomial, two-termed expression. If I multiply the 2, this 2 by this negative 2, I would get a negative 4. All right. So the only one that has a binomial containing a negative 4 would be this choice. So you could kind of logically play it out without doing any of the work. So the beauty of the multiple choice questions. All right. Some folks had trouble with the next one, but not so much because of the act of multiplying, more so because of the signs and combining like terms. So 4c plus 3, 5 minus 2d. This kind of problem is more like a concept check. Do you understand what you're doing in terms of distributing? Double distributing, it really doesn't matter. Actually, distributing any polynomial is the same concept. You take each term of the first polynomial and multiply it by each term of the second polynomial. Right? It doesn't matter what they look like. It's the same act. You do the same thing every time. All right? So the 4c gets multiplied by the 5. So that 4c could be thought of as 4c to the first, 2d to the first. But you're not going to have any like terms to compare to put together anyway. So if you neglected that, that would have been fine too. All right, so the 4 times the 5 will give you 20c. This is where people got jammed up. The 4c times the negative 2d. All right. Well, 4 times negative 2, that's going to be negative 8. C times d, well, they don't have a common base. So there's no keep the base, add the exponents. So you just put them together. All right. So if I have x times y, the result is just xy, unless I know what one of them is, or are. So 3 times 5, 15. 3 times negative 2d. 3 times the negative 2 part is negative 6. And then you have your d. D comes along for the ride. And there it is. So you just look for the choice that matches that. When you have multiple variables, like you see here, we don't typically have to worry about descending order. You'll notice how in the first two problems, we have the power of 2, then the power of 1, and then no power at all. Well, power of 0, really. In this case, we don't. It's not really structured that way. So we're not really overly concerned with descending order, but you got to be prepared for that. All right, so just making sure I check the right one. It looks like it's the last one here. This one's having you go the other way. All right, so it's kind of a brute force thing. You have 4 choices that could distribute out to give you the x to the 4th minus 12x squared plus 36. This was similar to number 1 in the sense that if you didn't recognize that x squared minus 36 and x squared plus 36 need to be written out a second time, then you would have dismissed those as possible choices. All right. So let me just go right to the correct answer real quick and show you why it's the correct answer. All right. So looking at the second choice there, we have x to the second minus 6 squared, which is really the same as x to the second minus 6. All right. Now, the reason I know that it had to be either the second or the 4th choice is because in the original problem, I had a positive 36. All right. What that means is that whatever these two signs are, whatever these two values are, I should say, they need to multiply, because, you know, when you do your double distributing, you multiply the first value by the first value by the last value, and so on. Eventually, you get to the part of the process where you multiply the negative 6, or whatever the last entry is, by the last entry in the second binomial. All right. Those two numbers needed to multiply to a positive 36. In the case of the first choice, these two values, negative 6, positive 6, would have given me a negative 36. In the case of the last choice, maybe it would have given me the right answer, but it looks like it would have given me a negative x to the 4th to start the whole thing off if I multiplied the last two terms. All right, so that would have given me the opposite of what I wanted. All right, but in each of these cases, even if I expanded this one out, x squared plus 6 times x squared plus 6, that would have still given me a 36, a positive 36. All right, so I can trim it down to 2 possible choices. The thing is with this one, just visualize it out, or just kind of imagine it with a couple of plus signs. If you look at this as if you suspected that this was the correct answer and you go to distribute it out, you would start asking yourself, okay, well, how am I going to get a negative out of that? All right, if the whole thing's positive, how am I going to get a negative in the expansion? I'm not. All right, so then by process of elimination, you come up with the correct answer. All right, so there's a logic to it, but you got to be willing to sort of embrace that logic. All right, but let's say you didn't recognize the logic and you were brute forcing. You went through the first choice, didn't work out. Second choice, 1x squared times 1x squared, 1x to the fourth, because remember you multiply your coefficients, add your exponents. Negative 6 times 1, negative 6x to the second. All right. Inner terms, all right, so the negative 6 times 1x to the second, negative 6x to the second, and then you have plus 36. And you see that the two middle terms combine. Remember, you keep, once you identify the like terms, you keep the variables the way they are, only combine the coefficients, and you see there we have the negative 12x to the second. All right. So that means that this choice was the correct one. All right. This one, it's a weird one, but basically it's another kind of brute force question. It just really depends on how you go about doing things. You can go from the original expression backwards, or you could go. I mean, we're not really there yet, or you can go from the original. The Roman numerals forwards, as in distribute. If you distribute, I'll just kind of talk you through this one. If you distribute the 2, you're going to get 4x squared minus 4x minus 120. All right, so Roman numeral 1 is good. All right, if you distribute in Roman numeral 2 the 4, you're going to get 4x squared minus 4x minus 120. So Roman numeral 2 is good. All right, which means that we're eliminating these two choices from possibility. All right, so the first two choices and the second and the third choice are out because they don't include Roman numeral 1, which we know is going to be correct. So it's a matter of whether it's 1, 2, and 4 or 1 and 2 only, which means I could ignore the weird-looking one. I could ignore that one, the most complicated one, because that's irrelevant now. So if I distribute, and so I'll just jump right to that part. So number 5, if I take my 4x, multiply it by x minus 1, subtract 120. So I'm taking my 4x, distributing it to each term here. I'm going to get 4x squared minus 4x. The minus 120 comes along for the ride. That's equivalent to the given expression. So now I know Roman numeral 4 is fair game, and so it has to be this choice. All right. So these two are just kind of like sight analysis. You just do a quick, all right, well, what would that give me? What would that give me? Because some problems you should be able to do in your head by now. Right? It's the more complicated ones where there's organizational strategies that come along the way. Those are the ones where you have to really kind of take a little time and diagram it out. But this, this is minimal in that regard. Even this part, if you're not there yet, that's what you should be working towards, being able to look at this and say, all right, well, let me just talk this out to myself. What would this be if I distributed the 4? 4x squared. And that would be minus 4x minus 1. Oh, that's what I got there. Okay, so it's 1, 2, and 4, and you're good.
So for a problem like this, you'd rather have us try to do it in our heads?
Yeah. Yeah. I mean, doing it on paper is fine, but we want to work towards doing it in our heads, because that's where you really start to take off with your understanding of this stuff. All right. This would be number 6, I guess. Oh, it says it right there. It's kind of a repeat problem. All right. It's another one of those questions where, all right, well, if you recognize that the binomial squared is, take that binomial and write it a second time. So that x minus 7, basically, let me just put it to you this way. The people who got this question wrong, they kind of made the same mistake consistently throughout the whole assessment. They looked at x minus 7 like this. I'll just show you what they did. They said x minus 7 squared And it's very typical. I mean, students, even in the higher levels of math, do this. So there's no shame in it. It's just something you want to get past. I mean, everybody makes mistakes. You just want to try to not be the one that's constantly making the same mistake. All right? So what students do is they take that x, they square it, they take that -7, they square it, and they say, well, that's what that's equivalent to. But that's not true. All right? Not true at all. All right? This is x minus 7 times x minus 7. And when you distribute it out, it's x squared minus 7x minus 7x, doing it a little bit quicker this time because it's basically the same problem that we did before, just with 7s instead of 6s, minus 49, or plus 49. So x squared minus 14x plus 49. All right. So that one recognition makes a big difference. I'm not a clever person when it comes to designing test questions. If I have a none of these as a choice, there's no hidden agenda. It's just because I couldn't think of another choice to put in. All right, other than like maybe x plus 7 in parentheses, then x minus 7. Just because you see none of these doesn't mean, oh, there's a none of these. It's the only one on the test. It must be the answer. It's almost never that. All right, it's not. There's no secret. It's just I couldn't think of another choice to put in there. In fact, that might be my way of saying it's hardly ever the answer. All right, so there you go. A lot of folks had trouble with this one. A lot of folks. This one's kind of a big deal. We have x plus 6. This is a benchmark's a bad word when it comes to this stuff. It's the only word I could think of right now. Because a benchmark makes it seem like, all right, are you where I need you to be, that sort of thing. But it's kind of like, if you can handle this kind of problem, what I call the right way, then you're in good shape. All right. So what I saw a lot of people doing in their work, and that's why I wanted the work, so I could see why you get it wrong. Why'd you get it wrong? I saw a lot of people taking this x and trying to multiply it by each term. All right. When you multiply, just thinking about if I asked you to multiply the numbers 2, 5, and 10, you probably do it pretty quickly. But my guess is that you took one pair of numbers, multiplied them, took that answer, and then multiplied that answer by whatever that last number was. 2, 5, and 10, you did it 2 times 5, 10. Then multiplied that 10 by the remaining number, 10, which gave you the 100. All right? It's no different when it comes to polynomials. All right? So I want to be looking at these 3 factors, but only 2 at a time. That's fine. But we want to look for convenience. We want to make our life as easy as possible. Now, earlier, I think it was 2 problems ago. Oh, I unchecked the correct answer and checked the wrong one. Not that that matters. I mean, I don't get a grade for it. But, I think it was the second question. Yeah. When you see a binomial pair that's structured this way, same expression but with a different sign inside, you know it's going to be a binomial as a result. All right, there's a name for it. We'll get to that in the next unit. All right. This pair of values here, 2 identical factors except for the sign. One has a positive, one has a negative. It's going to simplify down to a binomial. It's going to simplify down to a 2-termed expression. So if I start with those 2, distributing, which the way it's structured, that's probably where I would start anyway, then I'm going to get a cleaner answer than I would get if I started with these 2. These 2, if I multiply, I'll get a trinomial. A trinomial against a binomial would be my next step, as opposed to The result of this would be a binomial against a binomial. Binomial against a binomial is going to be easier than binomial against a trinomial. Right? So it's a matter of efficiency also. So I take my x, multiply it by x and negative 6, so x squared. Remember, x times x is x squared. That the number of times I circled the first term in an expansion, I lost track. All right, it was a very simple mistake, and I don't think it was for lack of understanding. I think it was just people just forgot to put a power of 2 there. So just be careful about little things like that. All right, the outer x times negative 6, negative 6x, positive 6 times x, 6x, positive 6 times negative 6, negative 36. Now you look at this and say, well, it's a 4-termed expression. What do you mean binomial? These two cancel out. So this whole expression becomes x squared minus 36. That's what I would take and multiply against the x plus 2. So I'm going to take my x squared multiplied by x squared multiplied by 2. So keep the base, add the exponents, x to the third plus 2x squared minus 36x minus 72. All right, so a lot of expressions that look pretty much the same. I mean, the only thing you could look at in terms of simplifying, making this a little cleaner in terms of how many choices you have, is that x to the third minus 72. If you're guessing, you're looking at that and saying, all right, that's either definitely the right answer because it's so different from the others, or definitely the wrong answer because they're so different from the others. So it was definitely the wrong answer because it was so different from the others. It was one of these three. It was just a question of the signs. All right, so 2 positives followed by 2 negatives. First choice. All right, then we get into the show all work stuff, or at least it should have been. And then we had that duplicated question, which we'll deal with, but this was simplifying. Fair amount of mistakes happened here, but based on what I was saying before, maybe we can clean that up because a lot of it had to do with the powers. The number one cause of error on this question, though, was how the final answer was represented. All right. So I just got to make sure I wrote the question down correctly, because that's my number one cause of mistake whenever I do math. It looks good, though. Let's get that towards the top. So I'm going to run through with an x. Now that x only applies to the first binomial, because coefficient, it's a variable coefficient, which is really kind of a contradiction in terms, but we'll worry about that later. X to the third plus 9x. This negative 2 gets distributed. So negative 6x squared plus 4x minus 2. Then this positive 4 gets distributed. Positive 4x minus 12. All right, so what I do, I mean, I have the benefit of the colorful markers up here and everything. Most of you are working with just, pens, pencils, whatever. But color helps, at least for me, because I look at this and say, all right, well, let me just grab any term, especially with the highlighters, any term that has that highest power of x to the third, or power of 3. Well, there's only one of them, so I'm going to write that down at the bottom. Then I look for the next highest power. Your answer needs to, when I say simplify, your answer needs to be in descending order. Highest power first, next highest power, all the way down the line. All right, so I have power of 3 accounted for. I now need power of 2. All right, so power of 2, I have one right here. I don't see one anywhere else. So my power of 2 is accounted for, minus 6x squared. Power of 1, that would be anything with an x, just an x. So I got a 9x, a 4x, and another 4x. Gives me a 17x. And then the only thing that's left are the loose constants. And the negative 2 minus the 12, that's going to give me a negative 14. All right. Most people did pretty good with this. People who messed up because of the powers and also because of the descending order. But it was very strange. The only power mistake that I actually saw was this one. For a lot of folks, that was for some reason becoming an x to the second power instead of x to the third power. And for a lot of folks, this term and this term were getting reversed. All right, can't have that. It's got to be in descending order. All right, so just be careful about little things like that, and you'll shore this up pretty good. All right, simplify, show, use any method. That would be the double distributing method. I didn't see too many people having trouble with this, and I feel like we've done like 10 problems like this already. It's the geometry method that people really are interested in. This question, if we have time, I'll come back and do it. But in fact, the geometry one was the same problem, and I can just check it by using that technique anyway. This one, answers really varied. So all you had to do is come up with 2 3-termed expressions that would give that as an answer. All right, so if you looked at this as, all right, well, I got something with 3 terms minus something else with 3 terms, and the answer had to be 4x to the third plus 3x, you have a pretty good framework. Like, for example, I can look at this and say, all right, well, let me start off with 6x to the third minus 2x to the third. That'll give me 4x to the third. If I can get this to kind of stay in the screen. Let me reset.
2x the second.
Thank you. I'll change that momentarily. All right, so I have that taken care of. It looks like I don't have, in my final answer, or in this jammy over here, I don't have anything raised to the second power. So I'd be looking at 2 power of 2 terms that would cancel each other out. So let's say I have, and so it really doesn't matter what they are as long as they're identical. So let's say it's 5x squared, 5x squared. I'll make them both positive. 5x squared minus 5x squared would be 0. So that would go away. So then using the same rationale, I would just need, the same rationale as the first terms, I would just need something that would give me a 3x. All right? So 2 like terms that would give me a 3x as a result. All right, so 7x and 4x. All right, 7x minus 4x would give you 3x. If you distribute this negative to that second trinomial, you'd get, so we'd have 6x to the third plus 5x squared plus 7x minus 2x to the third minus 5x squared minus 4x. You'd have like terms all over the place. This pair would give you the 4x cubed. This pair would zap away to 0. And this pair would subtract to give you a 3x. All right. It was supposed to be, I don't want to say a gift, but it was supposed to be sort of like a nice question that most people can get right as long as you understand the concept of like terms. All right. So if you interpret that as a gift, then by all means. But then we have the rectangle squares question. Most people struggle with this one. There were a few people who got it perfectly right. I think 1 in this class, 2 in this class, and then like 1 throughout the rest of the day. Perfectly fine. We haven't done it in a while, and we didn't do it for a whole heck of a long time, but the structure of it is pretty straightforward. You just got to remember the structure. So we have 2x plus 3 and 3x minus 2. So we start off with a big old rectangle. I'm sorry, big old square. We'll use squares and rectangles. It's a little more rectangle-y than I would like, but what we need to do is have each of these expressions represented as a dimension of the square. So I'm going to go down the line here. I need 2 x's. All right, so I'm going to call this distance x. Maybe a little longer. Doesn't matter. I'm going to call this distance x. All right, so every distance of that length is now x. So I need 2 of those. Down the vertical, and 3 of those across the horizontal. Draw our lines. Best you can. Rulers are wonderful, but not necessary. All right, the area of each one of these boxes here is based off of the dimensions that we just developed. So x squared, x squared, x squared, x squared, and so on. All right. Down that vertical, we also need to account for the 3 single units. So I'm going to decide on a certain distance that I'm going to call 1 unit. All right. That should be, well, I have this available space left over, so 1/3 of that should be 1. All right. So 2 of the x's plus 3 of the single units. The weird part of this, I'll admit it, that -2, that might have thrown you for a loop, but we treat that the same way. So whatever this distance is as 1, we're just going to label it with a -1. All right. And it's kind of strange to think of it that way, but you can have negative distances in geometry. It just doesn't factor in, especially when there's variables involved. It's a matter of movement. So when you're talking about a displacement, like I can take 1 step forward, that would be a +1. I can take 1 step backwards, that would be a -1. All right, it's still 1 unit. It's an absolute distance of 1, but the motion is dependent on direction. All right. So in this case, I mean, if you really want to think about it physically, this 1 would represent going in that direction, for example. And this 1, if we're actually, sorry, I got that one backwards. If we're establishing 1 as being to the right or up, then this would be plotting in the upward direction. And this one would be plotting this line segment in the leftward direction. I mean, it doesn't really impact anything in terms of the solution, just in case you were wondering. All right. So then we go through and we label it all up. We have an x by 1. So x, 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 x. Then we have here x by -1. So -x, 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 -x. And then over here, we have a 1 by a -1. So -1, -1, -1, -1, -1, -1. Add them all up and you have your area. And therefore, the result of the distributive property here. So I have 6 of the x squares. I have 9 of the blue x's, but then I have to remove 4 of the x's from that. So we're down to 5 x's. And I have -6 as a total for the single unit squares. No, not staying on the page again. All right, and that's what you would get if you distributed this out. All right, 2x times 3x would give you 6x squared. All right, so that would be the first terms. The outers would give you the negative 4x. That's this piece. The 3 times 3x would give you this piece. And the 3 times the negative 2 would give you this piece. All right, so it's all there. It's just different. All right. But this is actually, I mean, it's an important concept. I mean, it's not me just kind of forcing this down, you know, like into the curriculum just for the heck of it. This is actually the justification for why multiplication becomes addition. Like why you're able to say, all right, well, I'm going to take the positive 3 and the positive 3 here and make it a positive 9x. So I had the 6x squared, the positive 9x, and just kind of lay it out here as, you know, we have a positive 9, but somehow it becomes a plus 9 operation. Minus 4x. So negative 4x somehow becomes minus 4x. Negative 6 somehow becomes minus 6. Right? This geometric approach is the justification for that. It allows us to understand why we're able to do this to begin with. Right? There's value in it. It's just doesn't always feel necessary. Right? But that's the idea anyway. And then this was the, duplication? Yeah, I accidentally put that one in twice. And then you were like, yay, I get full credit on this. And then it's like, bonus question. No, it wasn't bonus question. It's just you had to do it. The trick on this one, most people didn't struggle too much. But be on the lookout for a power of 0. Makes things a whole lot nicer. All right, power of 0 is a beautiful thing. All right, so that means that for this one, we're just chopping off the middle part here, calling it 2x to the second. We have that cubed. Then we have the 5x to the second yz squared. When you're dealing with these monomials, recommendation, go through, even if you're comfortable, it's a test. You know, even if you're comfortable, go through and just jazz it up with all the coefficients and the exponents. Just so you don't miss something. 2 to the third gives you an 8. Multiply your exponents. So x to the sixth. 5 to the second gives you 25. Then multiply your exponents. X to the fourth, y to the second, z to the second. So we're looking at 200, x to the 10th, y to the second, z to the second. All right. If you came up with one of the 1600s, all right, one of the ones that had 1600, it's probably because you missed the power of 0. All right. I had the people who got this wrong. They treated the power of 0 like it was a power of 1. They're just like, oh, it's not there. And then they multiplied by 8. Then they threw in an extra x, an extra y to the third, and an extra z. And that messed things up. The lesson learned here is a careless error, or even a conceptual error in this case, is often going to be a choice. So you don't want to take that chance. So you got to be meticulous. All right.